Good afternoon, all. All are requested to be back at the earliest. We are about to begin the afternoon session. Thank you. Once again, good afternoon to all. So we are about to begin our afternoon session. So towards the session, once again, I welcome Jisha Mariam ma'am to handle the session. Thank you, ma'am. Over to you, ma'am.
Thank you. Is it visible?
Yes, ma'am. It's visible.
Okay, yeah. Welcome back. Then in the morning, we were discussed about the supervisory learning regression. The one of the supervised learning algorithm regression. Then we move to the another supervised learning technique classification. What is supervised learning? In supervised learning, we have the data and we already know the labels for each of this data. We know the output category of these data set. Okay, that is why it is known as supervised learning. And one category, one algorithm comes under supervised learning is classification. And there are several algorithms for classification. And one is first we are going to discuss k nearest neighbors, KNN. Suppose here we have several data points and since it is supervised we know which of the points are red and which of them are blue. Okay, we have the data points and we already know which one is red and which one is blue. Then suppose a new data point comes, then how can we identify whether it is blue or red? How can we tell? Okay, so is it possible to predict this point is blue or red, blue or red based on the available data, right? For that, we can consider the nearest neighbors of these data points. Okay, then in these data points, uh, here in this we will check, after considering the neighbors of this data point, we will check how much how majority of the neighbors belongs to which class. In this example, majority of the data points belongs to blue, so we can categorize this data point as blue. Then, and since we are considering its neighbors, k nearest neighbors, this algorithm is known as KNN, k nearest neighbors. Then how can we choose the value of k? If we, for example, if our value of k is 5, then we will consider its k nearest neighbors. K neighbors we will consider. Then we will check the majority of its neighbors belong to which class. Depending on that, we will categorize this belongs to either red or blue. Then in this example, we consider 5 neighbors and 3 of them are red and 2 of them are blue. So we can categorize this data point belongs to red. Okay. Then how can we define, or how can we identify these 5 neighbors? Here I am considering, I am taking k as 5. That means I am going to take these points 5 neighbors. Then how can we identify these neighbors? This can also be the neighbor. This point can also be the neighbor. Then how? Based on the distance between the data points, right? So for that, we required a distance measure to measure to quantify the distance between these 2 points. And we have several measures are available. One is Euclidean distance. It is quantified by square root of x1 minus x2 the whole square plus y1 minus y2 the whole square. This is a commonly used one. And another one is Manhattan distance. Here we will take the modulus of difference between the data points, like modulus of x1 minus x2, that will be this distance. Then modulus of y1 minus y2, that y2 minus y1 will be this distance. So the total distance will be sum of this line plus this line. It is known as Manhattan distance. And another one is Minkowski distance. It will be p root of x1 minus x2 the raised to p plus y1 minus y2 the p. Then the classification, the KNN can be used for both classification and regression. Okay, in classification we will consider the k closest points to the data, the newly data. And then we will check out which category of the in the most of the neighbors belong to which category. Then we will assign the newly coming data to that class, and this is known as majority voting. Okay, in classification, what we are doing, we will consider the k closest point of the tested data. Then we will check the class of the neighbors of these data and assigns the majority of the neighbors class. Okay, then what about the regression? In regression, the algorithm still looks for the k closest point, but instead of voting for the majority of the class, we will take the average values of these k neighbors. Then this average value will be assigned to the new point. Okay. In classification, we will take the majority voting. In regression, we will take the average of values of k neighbors. Then this average value will be assigned to the new point. Then KNN is also known as lazy learners. This is because in KNN, there is no need to build a model beforehand. We have the data, we know the labels of each of this data, we know the values of this data. Then when a new data comes, we will just store the data and make the predictions of this data, make the predictions of this data, tested data for the testing data based on the labels of the neighbors. Okay, but for the large data set, this KNN algorithm will be slow. Then, especially in high dimensional data, calculating the distance metrics become less meaningful. So it will reduces the effectiveness of KNN algorithm. So in that case, in order to increase the effectiveness of KNN algorithm, you can use different dimensionality reduction techniques. Then another important question is how to choose K. Which value we can choose for K? For example, if we some
Hope it's a connectivity issue. Please be patient. Hello, ma'am. Disha, ma'am, are you there? Hope she could join back soon. Hello, all. Extremely sorry for the connectivity issue. Our guest is joining back. Please be patient. Thank you. Hello, ma'am.
Am I
Usha, ma'am.
audible?
Yes, ma'am, you're audible.
Hello?
Yes, ma'am, you're audible, ma'am.
Am I?
Yes, ma'am, you're audible.
Okay, okay.
Kindly proceed, ma'am.
Okay, then how can we choose the value of k? Um, the value of k can be decided. The value of k will decides how many neighbors the algorithm looks when we are going to predict. Then choosing the right k is important for getting good result. If the data can make the predictions more stable. So, but if k is too large, the model may become too simple and it may miss some important patterns, and this is called underfitting. Missing some important pattern is known as underfitting. So, how can we fix the value of k? For that, we have different methods, and two of them are, one is elbow method and second one is taking odd values for k. In elbow method, we'll draw the graph showing the error rate or accuracy for different values of k. Then as k increases, the error will be, initially the error will drops, but after a particular point or after a particular value of k, it will be change the direction, the curve's shape will be changed. So that point is known as elbow. So plotting the curve between the different values for k and error rate is a one method for selecting k, for fixing the k. And another method is choosing it is better idea, it is a good idea to use an odd number of k, especially in classification problem, because if we choose k as 4, then for the point we will consider 4 neighbors, right? Then among these 4 neighbors, if two of them are in class 1 and another two of them are in class 2, then how can we assign or how can we decide the newly point will belongs to which class? This will make some problem if we take even number of k neighbors. So it is better to go with odd number of neighbors. Okay, this will break, it will avoid the ties when deciding which class is the most common among the neighbors. Okay, these are about the KNN algorithm. In KNN is a classification algorithm, mainly classification algorithm, which comes under supervised learning. Here we have the data with the labels, and if a new data point comes, we want to predict we want to predict the class of this new point. For that, we will consider the k neighbors. Among k neighbors, we will count the majority of the neighbors class. Okay, then we will assign that class to the neighbors. If our problem is a regression problem, then we will take the average of values of these neighbors, then assign that average value to the new point. Then in order to calculate the distance, in order to identify the neighbors, we use distance measures. Different distance measures are there. Then selecting the k value, we can use, one is elbow method and another one is considering the odd values for k, and plot the graph between the k values and accuracy rate. Okay, this is about the KNN algorithm. Next, mm, Actually, I am not able to present. Yeah, now I can try.
It's okay now, ma'am.
Yes. Then now we move on to the probability theory for like maximum likelihood estimation and maximum a posteriori estimation. Before that, we can go through the probability theory. Probability is a mathematical framework that allows us to describe and analyze some random phenomena. In random phenomena, the event or experiment will be, we don't know the outcome of a particular event or particular experiment. That can be considered as a random phenomena, and probability theory is mainly used to describe such kind of random phenomena. Then when we say that something is random, we are saying that our knowledge about the outcome is limited, so we can't certain what will happen. Okay. Then random experiment is a process by which we can observe something uncertain, and the result of the random experiment is known as outcome, and the set of all possible outcome is known as sample space. Then even a particular event will be the collection of these possible outcome, and that will be the subset of our sample space. Then the then the event is a subset of sample space, and to which we will assign the probability, and the value of the probability will be always in between 0 and 1. That shows how likely the event is. Then the random variable can be a real world variable whose value is determined by some random experiment. Okay. And that random variable x can be either discrete random variable or continuous random variable. In discrete random variable, the x is discrete random variable, that means that x can take a particular specific value. In that time, we will use the probability mass function or probability distribution, which gives the probability with which each value is assumed. But coming to continuous random variable, it will take the random variable can take uncountable infinite number of possible values. That means if the random variable is continuous in the sense that the probability of getting a particular value will be 0, because it can take only values are there. So usually in continuous random variable interval a and b, that will be calculated as probability of a less than x less than b. That means the value of x will be in between the range a and b, and that will be evaluated using the probability density function. And if the then if the distribution is discrete, we can plot like that. But if our random variable is continuous, then we will use the probability density function. The probability that this is the second one is the when the first figure shows the distribution that when the random variable is discrete, and the second one is when the random variable is continuous. Then the probability that the random variable x takes a value interval a and b will be the area above this interval, that is, this is the interval a and b, area above this interval and under the graph of the probability density function. Okay. Then for any point a, if our random variable is continuous, then probability that random variable will take the value a will be equal to probability of a less than or equal to x less than or equal to a. That means it will be the integration from a to a f of x dx, which will be 0. That is why we are telling that in continuous random variable, it can take always we can specify always the range of values. We cannot assign a specific values. In that case, the probability will be 0. Then the probability density function PDF of random variable x is a function f of x such that For any two numbers A and B with A less than or equal to B, we have the probability that X will be in the range A less than or equal to X less than or equal to B equal to is calculated by the integral from A to B f of X dx. Here the f of X is a probability density function. Okay, then probability that X is in row A can be calculated by integrating the probability density function with respect to X. And here this is an example. Here this blue colored region, blue shaded region indicate probability that the variable X will takes the values from 0.20 to 0.3, and this area under this curve will give the probability. Okay, then the distribution function of a continuous random variable will be looks like f of X is equal to probability of X less than or equal to X integral minus infinity to X f of u du. Okay, and where the function f of X has the properties when f of X greater or equal to 0 and integral minus infinity to infinity f of X dx equal to 1. If these two criteria, these two requirements are satisfied, then that function is called probability density function. For a probability density function, the criteria are its values will be always greater than or equal to 0, and their integral from minus infinity to infinity will be 1. Then we are moving to probability term to the likelihood term. Here we have a probability that a randomly selected object will in between 32 and 34 grams. Okay, so here we have the distribution with the mean 32 and the standard deviation 2.5. Okay, for a distribution, the two parameters that are required to describe the distribution is mean and the standard deviation. So here the 32 is the mean and standard deviation is 2.5. Then probability that a randomly selected object will weigh in between 32 and 34 gram can be considered or can be calculated by the area under this curve in between 32 and 34. For a probability, the distribution, can be calculated by probability of weight in between 32 and 34, given that the mean of the distribution and standard deviation of the distribution. Okay, here we are going to calculate the probability that the weight between 32 and 34, but we have the condition, we have some known things. What is that? Given that mean and standard deviation, the parameters of the distribution are given. Okay, using this given data, we are calculating what's the probability that the weight will be in between these two range, and it will be calculated by area under the curve. In this example, it will be 0.29. That means 29% chance that a randomly selected object will weigh in between 32 and 34. Okay, then that means assume we have a large already a weighted object. Then we are moving to the reverse of this thing. Here we know the distribution of the parameters of the distribution. Then we are finding out the probability. Next thing is we already have the weighted object, and the weight will be 34. Okay, then calculate the likelihood of weighing a 34 gram object that which belongs to the distribution. That is represented by L likelihood, and here we know the object weighs 34 gram, and what is the probability that it belongs to the distribution with the parameters mean is equal to 32 and standard deviation is equal to 2.5, and that will be calculated on the y-axis. In summary, the probabilities are the areas under a fixed distribution. If we have the distribution and we want to predict the data will be in this particular range, in that case we can use the probability as the area under this curve. Then again the reverse thing, we have the data and we want to find out the parameters of the distributions. This will be similar to the likelihood. Here the likelihood are the y-axis values for a fixed data point. Here the data point is fixed. The given data is a data point. It is fixed, and we need to find out the distribution that belongs to this data point. It will be on the y-axis, and it is known as likelihood. So for example, if we have a set of data set, And each of these data point, we will plot the distribution. We will check the distribution, or we will calculate the likelihood of the each of these data point. Then the point that gives maximum likelihood will be the appropriate distribution of our data set. Okay. Then, and that means maximum likelihood estimates for the mean and standard deviation. Maximum likelihood will help us to identify the parameters such as mean and standard deviation of the distribution of our data set. Then how can we calculate the likelihood? Likelihood can be considered as a reverse probability. That means we can consider here we have the observed outcome of the experiment, and we need to find out the parameters of the distribution, which is same as we have the distribution parameters theta. We want to predict the probability of the data point x. Okay. Then if we have multiple variables, multiple independent variables, then we can consider the likelihood of theta given that such x1, x2, xn, which is equal to probability of the points x1, x2, etc., xn, given that the parameters of the probability density function. Then for maximum likelihood estimation in my MLE, we have different probability distributions such as binomial distribution, normal distribution, exponential distribution. In each of these distribution, the parameters are different. In binomial distribution, the parameters can be the mean and the standard deviation. And in coming to like n and p, and normal distribution, the parameters may be mu and sigma square. And exponential distribution, we have only one parameter, lambda. So in order to find out these parameters of the probability distribution, we will check the maximum likelihood of the observation. Okay, we have the data and data drawn for an exponential distribution. Then question is which exponential distribution? Then which exponential distribution? That question is answered by depending on the parameter. We want to identify the parameter that most likely to the available data. That means for which parameter value does the observed data have the highest probability. That is why it is known as maximum likelihood estimation. Then these are the different distribution function and its characteristic function. Depending on the distribution, the parameter values are varying. We want to calculate these parameters which looks most likely to the real data. And the likelihood, if we consider that our features are independent, then we can calculate the likelihood as the product of the terms. Product likelihood of the parameters theta equal to probability of x1 given theta, probability of x2 given theta, such that way. Then for the ease of the calculation, we can take the log on both sides. Then this log will allow us to take just as a summation. The same thing we are doing in the logistic regression. And then if our probability density function is Bernoulli's density function, in Bernoulli's case we have only two classes. The probability of one class will be p, then the probability of another class will be 1 minus p. And the equation can be simply putting like that, probability of x given p is equal to p raised to x into 1 minus p raised to 1 minus x. Here x can be either 0 or 1. And then another probability estimate, another thing based on the probability is maximum a posteriori estimate. Here this ML, how it is different from ML. In actually MAP, it allows a prior belief about the candidate models to incorporate systematically. And for example, what is mean by prior belief? Here A indicates the event that we sell the ice cream. Okay, then we indicate the event of the weather. Then what is the probability of selling ice cream given a particular type of weather? Okay, probability of A equal to selling ice cream given a particular type of weather. And according to Bayes' theorem, this can be calculated by probability of A given B as probability of B given A into probability of A by probability of B. Here the probability of A, that means probability of sale of ice cream. It is before, we know that thing beforehand. So that is why it is known as prior belief or prior probability. P of A is known as prior probability. Okay, but P of A we already know, but in addition to P of A, we required some condition in form of B. Okay, that is why P of probability of A given that some condition B. Okay, and we already know the probability of occurrence of the event A, and that probability is known as prior probability, prior belief. Okay, and if 30 people out of potential 100 actually bought ice cream, then we can say that probability of selling ice cream can be 30 by 100, which is equal to 0.3. And this can be considered as a prior to knowing anything about the weather. Before knowing the particular weather, we know that probability of selling ice cream can be considered as a 0.3. And this can be considered as a prior knowledge. And using the name, and another quantity that we want to calculate is the posterior probability. That means probability of A given B. This quantity we need to calculate using prior probability P of A. And P of A given B is known as posterior probability. And the normalizing constant P of B, it will be constant. So we can simply remove, and we can say that probability of A given B is directly proportional to probability of B given A into probability of A, the numerator part. Okay, and this is similar to the maximum likelihood estimation with the addition of prior probability over the distribution and parameters. The same thing, the Bayes concept can be converted to our maximum and posteriori probability estimation. Then our aim is to maximizing this quantity over a range of theta values. Then then solves the optimization problem using this technique is known as maximum posteriori estimation. Okay, then from this point we can move to the Bayes concept.
Okay, it's visible, ma'am.
Thank you. Then we are moving to the Bayes classification algorithm. Initially, we discussed the KNN classification algorithm. Then we move to the Bayes. Next one, Bayes. Here, suppose we have a set of shapes and with the different colors. Then what's the probability that the selected shape, so if I am selecting a particular shape, particular thing randomly, what is the probability that it is a star? We can calculate that among, here total we have 10 shapes, then among these 10, 3 of them are star, right? So probability probability that the selected one is star equal to 3 by 10. Then again, what is the probability that the selected shape is green? Here, among the 10 shapes, 4 of them are green. So the probability will be 4 by 10. Then again, what is the probability that the shape is star given that it is green? Okay, P of star bar green means probability that the shape is star given that it is green. Then how can we calculate the probability? Which is equal to total green stars, okay, divided by total green shape, because we already know, we have the data that the shape is green, so we only need to consider the green shaped things, right? So total green stars divided by total green shapes, which is equal to 2 by 4, because here we have 4 green shapes. So 4 out of 4 these shape, only 2 are star. So our probability of selected item is star given that it is green is 2 by 4. The same thing we can perform. The probability of the given shape is green. Given that it is star means probability of the shape is green and star divided by the probability of the shape is star. The same thing, the reverse thing we can happen. We can write. And Bayes theorem helps Bayes theorem helps you examine the probability of an event based on the prior knowledge of any event that has correspond to the former event. Its uses are mainly found in the probability theory and statistics. This is the Bayes theorem. Here, probability of A given B. It gives the probability of occurrence of the event A given that the event B is true. It is already occurred. We know the probability of this P of P. Yeah, so this event B is known as evidence. Okay, so this P of A given B is the probability of occurrence of event A given that the event B already occurred. Okay, then which can be calculated as probability of B given A into probability of A by probability of B. Here the P of A, probability of occurring the event A, is the prior probability, because prior probability, that is probability of the event before the evidence is seen. That means here the evidence is P. Okay, so before the evidence is seen, what is the probability that the event A will occur, and it is known as prior probability. Then probability of B is the prior probability of B before the evidence is seen. Then next one is P of B given A, probability of occurrence of the event B given that A is the evidence A is seen. Okay, this is the Bayes theorem. Here the probability of A given B is known as posteriori estimation, and probability of A is the known thing before the evidence is seen, so it is known as prior estimation. Then suppose we can have multiple events like x1, x2, etc., xn. That time we can calculate the probability of the event A such that given that we have the features x1, x2, etc., xn, which can be calculated by probability of occurrence of these specific values of features given that the occurrence of event A is true into probability of A divided by probability of x1, x2, etc., xn. Okay, suppose for example, if we have 3 features x1, x2, x3, then it can be calculated by probability of occurrence of A given that we given some specific values of x1, x2, x3, which is equal to probability of x1, x2, x3 given that A is true into probability of A divided by probability of x1, x2, x3. Okay, the same thing. If we in the one assumption for naive Bayes is that the features are independent, they are conditionally independent in the class A, then this probability of x1, x2, x3 given A can be calculated as the multiplication of each of this probability, like P of x1 given A into P of x2 given A into P of x3 given A, and substitute this thing into the equation. The newly equation will be like this way. Okay, then the denominator, probability of x1, x2, x3, it will be same for all the classes. So this portion, this denominator is same for all the classes. So we can simply ignore this term because this is equal. So the probability of occurrence of A given x2, x3, x1, x2, x3 is directly proportional to this part, this numerator part. That is why we written as probability of A given x2, x3, x1, x2, x3 is directly proportional to probability of A into probability of x1 given A into probability of x2 given A into probability of x3 given A. In general, suppose we have n features, then probability of occurrence of class C with the specific features x1, x2, etc. xn can be written as probability of occurrence of class C into product of probability of occurrence of each of these features given the class C divided by probability of occurrence of the features. And as we already said, this term, denominator term, we can neglect because this probability will be same for all the classes. So this probability of occurrence of class C given the features, particular set of features, will be directly proportional to probability of C into product of these features given particular class C. Okay, then the example here we have the data of 8 days and the features are outlook, humidity, windy. And the outlook can take the values sunny, overcast, rain. Okay, then humidity can take the values high or normal, high, normal, low. It can take three values, high, normal, low. And the windy can take either true or false. Okay, so here we have the data of 8 days and three features are there: outlook, humidity, windy. And outlook can take three values: sunny, overcast, rain. And humidity can take the values high, normal, low. And windy can take the values false, true. And here our output label is play, and it can take the values only yes or no. Then suppose we got a new data. Is it visible? Is it clear now? Okay, here we have a new data with the outlook is rain and humidity is high and windy is false. Okay, then whether suppose we want to predict whether a particular play like football or tennis, whether the play should be played or not. So that means we want to predict what is the probability that the play should played given the outlook as rain and humidity as high and windy as false. The same way, we want to calculate the probability of the play should not be played with the given outlook rain humidity as high, and windy as false. Then after calculating the probability of these two classes, here we have two classes, yes or no. Then after the probability of occurrence of these two classes, we will calculate which one is greater. That will be our answer. Then how can we calculate this probability? This is the equation. Probability of S given that rain, high, false. These are the specific values of our features. Using these specific values of the features, we want to calculate what's the probability that the football should be played. Then again, with these given specific values of features, what is the probability that the football should not be played? Okay, then for first case we will calculate it as we assume that our features are independent, so we can separately calculate them, and we can multiply it. Okay, then probability of rain given as into probability of high given as, probability of false given as into probability of S divided by probability of rain, high, false. Then the second case, probability of rain given no into probability of high given no into probability of false given no into probability of no divided by probability of rain, high, false. Then we are going to calculate each of these. The first one is probability of S. Here we have total, we have 8 datas, right? So out of these 8 datas, 5 of them are S. 1, 2, 3, 4, 5, right? So 5 of them are S. So the probability of S will be 5 divided by 8, which is equal to 0.625. Then next we want to calculate what is the probability of occurrence of the class no. So out of these 8 classes, not 8 classes, out of these 8 datas, 3 of them are in class no. So the probability will be 3 by 8. Then next we want to calculate the probability of occurrence of rain given that the class belongs to S. So we will check this combination. For the given condition is class S, the class belongs to S. Here we have 5 classes, 1, 2, 3, 4, 5. Yeah. Among these 5 classes, how many of them are rain? 1 and 2. So the probability is 2 divided by 5. Then the next one, the probability of rain given that the class is no. Out of 3 no classes, the rain comes under only one condition. So the probability is 1 by 3. The same way we will calculate the probability of high, the second feature, humidity. Humidity, it will be high with a given class S. So we will look into out of 5 S's, how many of humidity are high? 1, only 1, right? So the probability will be 1 by 5, which is equal to 0.2. The same way we will calculate the probability of the feature becomes high given that the class is no. And probability of false, probability of the windy becomes false given that the class is S. Again, the probability of windy becomes false given that the class is no. Then after calculating, we can simply substitute these values into the equation. Then we will get a probability of the football should be played with a given condition rain, high humidity and windy falls is 0.0200. And the second one, probability of football should not be played with a rainy condition, high humidity and windy falls is 0.0277. Then we will compare these two values. Among these two values, the second one is higher. So the probability will be game should not be played. This will be the probability. This will be our decision. because this probability is high. So our decision is game should not be played. Then another example, here we have the data set, and the feature with the features, color and shape. Okay, then and here our prediction should be either it is positive or negative. Okay, then here our input is, our shape is square and color is blue. Then what is the probability that it will be plus, it will contain plus. Okay, so same way we will calculate probability of occurrence of plus, given that the color is blue and shape is square. Then you can use the same equation for neighbors. Then we will calculate the probability of occurrence of negative sign, given that the color is blue and shape is square. Then we will calculate the values and compare. After comparison, we can identify that this probability is higher. That means this sign will be plus. This box will contain the sign plus. Okay. Then another issue with this, what happened? An issue that arises in the calculation is what to do when evaluating a feature value you have not seen. That means in this data set, we have the colors red, blue and black. What happened if the color is orange? Our newly tested data having the color orange. Then of course the probability will be 0, because according to our data we have no such a color, right? Orange is not available in our data set. So when we calculate the probability with this data, it will be 0. So in order to avoid that, we can use the technique Laplace smoothing, which is used to avoid zero problem. That means in according to Laplace smoothing, what we are doing is, here what we are doing, probability of occurrence of plus sign, given that the color is orange and the shape is square. But here we know that there is no existence of orange color. According to our data, we have no orange color, right? So when we calculate the probability of orange, given that symbol is plus, it will be 0 by 7. So in order to avoid the probability becomes 0, we will add value to the denominator. We will add the number of values available in this class. That means red, blue, black, and again we will add the one more color, orange. Okay, that will be plus 4. And in the numerator we will add a symbol, we will add 1. Okay, the numerator we will add 1, and denominator we will add the number of values in that particular feature. This will avoid the 0 problem, and this is known as Laplace smoothing. It is mainly used for avoiding the 0 probability. Then we will calculate the probabilities. Then after that we can find that the probability of occurrence of plus sign is high. So we can group them into the plus sign. Okay. Then Naive classifier can be used on discrete features. Then what about the continuous features? In our examples, all these are discrete features, like the value can be fixed, like either it is sunny, overcast, false, true, no, yes or no, high, normal. All these can be considered as discrete features. Here also it is discrete features. But what happens if the features contains the continuous values? Like the humidity will be like a set of numbers. Then in that case, we can use the probability density estimation, and to estimate the parameters of that probability density function, we assume that the distribution is event model. We can assign the distribution, and that means here in this example, here the features refund, marital status, taxable income. These two features, refund and marital status, these are discrete features, but the taxable income is a continuous feature. So in that case, we assume that this continuous feature follows the normal distribution. Okay, then we will calculate according to the normal distribution. We will calculate the probability of occurrence of A, one for A, given that the class C. We will calculate this for each pair of AI and CJ. Then, for example, for income, for a specific value of income, what is the probability for what is the probability given that the class is no, and what is the probability that specific value for the for the income. If class is equal to no, the sample mean and sample variance we can calculate from this distribution, and that means probability of income equal to 120, given that the class is no, will be 1 by root 2 pi sigma, then variance e raised to ai, that means the attribute value. Here the income is 120, attribute value minus mu ij, that means mean, sample mean. The mean of these distribution is 110 divided by 2 sigma square. Okay, this will be the probability. So if our feature is if all our features are not discrete, if some features are continuous, then you can use Gaussian nairs. Identify the distribution of that continuous feature, then put your formula. Then coming to multinomial based classifier. In multinomial based classifier, it is a variation of database algorithm mainly designed for discrete data. Gaussian database is mainly for continuous data, continuous features, but multinomial database is used for the discrete data. It is mainly used for text classification, where here the features will be the word count or number of word frequencies. So and this multinomial based classifier is commonly used for spam detection, document classification, and sentiment analysis. Here we have the document. From this document, we will collect an unordered set of words with their position. We will simply ignore the position in this document and only keeping the frequency of these words. Okay. Then for a document D, we have C classes. So out of all the classes, the classifier returns the class which have the maximum posterior probability for this document. That means this document belongs to the class C, which will be based on which class will have the maximum posterior probability. Then we can assign this document to that particular class. Then this is an example. Here we classify a message as spam or not spam. This is our class. Either it can be spam or not spam. And these are our, here we have 4 messages, and this is the message text. Then we classified each of, we already know the class of each of these message. Then firstly, extract all unique words. As a first step, we will extract all unique words from this data set. Okay, so the vocabulary will be from the first message we will extract the words by, cheap, now. Then from the second message we will extract the word limited, offer, by again by already we included. Then meet, me, now already included. Next word let's, catch up. So the size of the vocabulary is 10. 10 words are 10 distinct, 10 unique words are identified from this data set. Then next step, count the word frequencies by class. That means in spam classes, how many times each of these word occurs. In spam class, we for the first word by. It occurs 2 times, right? Here, here. So count is 2. And the second word cheap. It in spam class it comes only on 1 time. So it is 1. Now 1 limited only 1 time, offer 1 time. So total number of words present under spam class is 6. 1, 2, 3, 4, 5, then 6. Right? By is occurred in 2 times. So total word count is 6. Then again the same process for second class not spam. Not spam classes are message 3 and message 4. Here also we will count the meet. Meet will occur only 1 time. Me occurred on 1 time. The same way we will count the occurrence of each word, and total number of words is 6 under not spam class. Then our test message is buy now. Then we want to classify whether this message text buy now is spam or not spam. Then for that we have the probability formula. Probability of occurrence of class C given the text message D is directly proportional to probability of class C into product of probability of occurrence of word I given the class, right? So the probability of occurrence of P of W C, probability of W given C can be calculated as count of W C plus 1 by total words in C plus V. And count of W C is the number of times word W appears in document C in class C. Count of WC is the number of time this word W occurred in class C. And N is the total number of words in document of class C, and V is the vocabulary size. So here in our example buy now, right? So first of all we want to calculate the probability of two classes. This is the equation. Probability of C, probability of spam is 0.5, because here we have four messages. Among these four, 2 are spam. So 2 by 4, which is equal to 0.5. The same way not spam is equal to 0.5, because 2 of them are not spam. So 2 by 4, 0.5. Then we want to categorize, we want to find out spam class, right? So probability of by, the first word is by, right? So probability of occurrence of by in spam class, given that class is spam, equal to the count of this word, which is equal to count of this word W. That means count of W in class C. That means count of this word by in class spam. Here you can see that by the word by comes 2 times in spam class. So 2 plus 1 divided by total words in class C. Total words in class C, the in spam class we have 6 words. So 6 plus then vocabulary 10. Okay. The same way probability of occurrence of a word now belongs to the class spam equal to the same. Using this equation you can calculate it as 2 by 16. Then after getting these two, we can find out probability of occurrence of spam, probability of occurrence of the class belongs to spam with the given message D as proportional to probability of the class spam 0.5 into multiply these two probabilities. Okay, the same calculation we can done for not spam classes. Then after calculating the probability of both the classes, we will compare which one is greater. Here we can see that this one is greater. So we can assign this message, text message, as a spam. Okay. Then coming to the next name-based algorithm, Bernoulli's name-based. It is typically used when the data is binary. And we here it is used for the classification of binary features such as either yes or no, 0 or 1, true or false, like that way. And the Bernoulli's, to understand how the Bernoulli's, here is a symbol, the equation for binary Bernoulli's base is probability of the conditional probability of occurring xi provided y is occur equal to probability of I given y into xi plus 1 minus probability of I given y into 1 minus xi, and I is the feature index, I is the feature index, and xi holds the either the value binary 0 or 1. And this is an example. Here, as the similar case, we have 4 messages and we have the class where it is classified as either spam or not spam. And first step is to identify all the vocabularies, then identify the vocabulary size. Then the second step is we will construct the binary feature matrix. Okay, and in binary feature matrix, the values can be either 1 or 0. 1 indicate this present, 0 indicate absence. Each message, that means here each message is represented using binary features indicating the presence or absence of a word. Or for example, the first message M1, the message 1 is buy cheap now. So we will put it buy as 1, cheap as 1, now as 1. And all other words are absent. So we will put zeros. And the second message, limited, offer, buy. Right? Here we will put buy is present. So 1, cheap now are absent, limited is present, offer is present. So we put 1. And all other words are zeros. And also we will specify the class. Then the same thing we will do for message 3 and message 4. Then we want to calculate what is the probability that here the equation for the probability word the word wi present in the document. That is why its value will be 1. Wi is equal to 1 means the word wi present in the document 1, and given the particular class C is calculated by count of number of documents in class C that contains this word wi plus 1 divided by total number of documents in C. That means total number of documents that belongs to this class C plus 2. And plus 1 is used for the Laplace smoothing in order to avoid the zero probability problem. And plus 2, since Bernoulli features has according to Laplace smoothing, in the denominator we will add the number of values of the features, right? So in Bernoulli we have only 2 features values. That is why we added 2, either present or absent. So only 2 values are available in the feature. That is why we add 2. If the feature have 4 values, then we will add 4 to the denominator. Okay. Then for the spam class, we will calculate the probability of occurrence of buy in spam and cheap in spam. The same way we will calculate all the probabilities, and the same thing we will do for not spam class. Then our text message is buy now. Okay, then the message contains the word buy and now. So the feature vector will be buy is equal to 1, now equal to 1, and all other features will be 0. Then for the spam, the probability of occurrence of the class spam with the given text message buy now is directly proportional to probability of spam into probability of buy is equal to 1 in the class spam into probability of now equal to 1 in the class spam. Okay, that we already calculated. Then simply substitute the values and we will get the value. Then for not spam also, we will find out probability of the occurrence of class not spam of the document buy now or of the message buy now is directly proportional to probability of occurrence of the class not spam into these factors that we already found. Then multiply, then compare both the result and found that this value is high, 0.1875 is high. So we can assign this, we can classify this test message as spam. Okay. With this, we wind up the naive-Bayes equation. In naive-Bayes, we discussed the basics. What is naive-Bayes equation? What is Bayes theorem? And then we tried some example. Then we discussed the zero probability problem. Then solution for zero probability problem is Laplace smoothing. Then for continuous features, we can use Gaussian naive-Bayes. Then for the text classification, we can use multinomial naive-Bayes. And then yeah, if the we can also use the Bernoulli distribution, Bernoulli naive-Bayes, when the features can be considered as a binary features. Binary, that means features can take only two values. In this case, we can use Bernoulli naive-Bayes. This is the example. Then we can move to the next topic. SVM. Next classification algorithm is support vector machine. We have discussed a KNN, K nearest neighbor classification. Then we discussed neighbors classification algorithm. Now support vector machine. This is a very vast topic. Here I just introduce within this short period of time. It will be difficult to cover the SVM in detail because it is very vast topic. So, SVM, support vector machine, SVM, it is a classification method. Here, the main task is to find out the decision boundary separating sample in one class from sample in another class. We need to find out the boundary, just like regression line. And it is binary in nature. Here we have only two classes. These are the data points. We have two different classes, and black samples are considered as positive classes and white points are considered as negative classes. Then we want to find out a line, a separating line. We want to find the best possible line separating these samples in one class from the samples in the another class. Okay. Then in 2D space, this decision boundary can be the line. Line is sufficient. But in the 3D space, we required a plane, which is known as hyperplane. Okay. Then, and support vector machine SVM can be linear or non-linear. Depending on the nature of the data sample, the decision boundary can be the linear one, and also it can be non-linear one. But usually what we are doing is non-linear thing. We'll be finding the non-linear decision boundary. It is a very complex process. So we will convert this non-linear problem into linear SVM problem. Then the task is to find a separating line, right? And as in linear regression, we can have multiple separating planes. There are infinite number of lines which can separate these positive and negative sample. Then which one of them will be selected as a good separating line? So therefore all the points in the hyperplane we can define the hyperplane as a function g of x, which is equal to w raised to t into x plus w0, and the x is the feature vector input data. Actually, this is the matrix representation for the line. In the first regression classes, I did not discussed or mentioned about the matrix representation of the line or the equations. This is the matrix representation here. Vector representation here, x is the feature vector input data points, and w is the weight vectors. That means our in our terms we can say that it is a parameters, and w0 is a bias or intercept, and g of x is the decision function, and g of x is our hyperplane separating these two data points, and all the points on this hyperplane g of x will be 0. Then for all the point above this hyperplane, we'll have the function g of x greater than 0. If this function g of x is greater than 0, then it will belongs to the above of the hyperplane. Then all the points below the hyperplane, g of x value will be less than 0. And if the point is on the line, it will be g of x will be 0. And if the point is above the line, g of x will be greater than 0. If it is below the line, then g of x will be less than 0. Okay, greater than 0, equal to 0, less than 0. If it is greater than 0, then we can consider it as positive samples. If it is 0, that means the point is on the hyperplane, hyperline. Then if it is less than 0, point is in the negative sample. Then we choose a hyperplane that has a maximum separating margin. Okay. Then here H is the separating hyperplane, and H plus we want to find out the maximum separating hyperplane, right? So H plus is the plane parallel to this hyperplane H and passing through the nearest positive points. Okay. Then H minus is the plane parallel to this hyperplane H and passing through the nearest negative point. And separating margin is the distance between this H plus and H minus. Then our aim is to maximize this margin. Okay, margin between these hyperplane. We want to maximize this distance. Okay, so we choose a hyperplane that has the maximum margin. Then finally, how can we find out the separating hyperplane with the maximum margin? Suppose let us take 2 points x1 and x2 that are lying on this equation. So if this x1 and x2 lies on the hyperplane, its value of g of x1 and g of x2 will be 0. Then simply substitute this value of x1 and x2 in our equation w transpose x plus w0. By simplification, we will get w transpose into x1 minus x2 equal to 0. This is a typo error. Then it means the weight vector is orthogonal. That means perpendicular to the vector x1 minus x2. Okay. So that means, in other words, this weight vector is orthogonal to the plane g of x. Okay. So then how can we calculate the margin between these two hyperplanes H plus and H minus? We want to find out the hyperplane that maximize this function, right? So for a given data point xi, yi, and yi can be either positive or negative. Let us replace these negative, we can replace these negative samples as +1 and negative samples by -1. Okay. So for each data point, we can classify that the data point can be either, if it is greater than or equal to 1, then it will be class to 1. If it is less than -1, then it will be class to the -1. And we can combine, for the ease of the calculation, we can combine these two equations. Okay. Then suppose if x1 and x2 are 2 points on the decision boundaries b1 and b2, then our equation will be weight vector into x1 plus b equal to 1 and wx2 plus b equal to minus 1. And we can combine these two equation. From this equation, this is a dot product of the vectors w1 w and x1 minus x2. Then from this we can calculate the distance x1 and x2 as 2 divided by norms of w, and it is calculated using root of w1 square plus w2 square plus wm square in m dimension space. So in SVM, we have the data n data points x1, y1, x2, y2, etc. xn, yn, where each x is the feature vectors. It consists of different set of features. And we have two classes yi. It can be either plus 1 or minus 1. Find a vector. Here our objective is to find out the weight vector. Our parameter is weights and the number b. We want to find out these parameters. That should be minimize the this distance 1 by 2 into norms of square, subject to the condition that this thing, that means the for this hyperplane, every point greater than or equal to 1 of this hyperplane, it will be classified to plus 1, and for every point below less than 1, it will be classified to the negative class. So subject to this condition. Okay, this is the overview. This is very small overview. Actually in SVM we have a lot of topics. This is only a small overview about the SVM. Then next I'm going to the another topic, evaluation measures. Yeah. Okay. Then till now we discussed different. In the morning session we discussed regression models. Afternoon we discussed different classification models. And how do we evaluate these measures? How can we compare or evaluate whether our model is good or not? For that, firstly, we can discuss the classifier performance. We can analyze the classification algorithms. For evaluating the classifier performance, we need to construct the confusion matrix. From the name itself, it is clear that it is a confusion. It is a matrix. It is in the form of rows and column. The rows can be rows and column. Rows can be the actual values, okay, and the columns can be the predicted value. Its inverted case is also present. It is not an issue. In this example we consider each row as the actual classes and columns as predicted classes. Okay, then if the matrix is k by k matrix, here it is 2 by 2 matrix, and the entry ij contains the actual number of samples that are in class I but predicted in class J. Clear? The entry ij in the matrix is represent the actual number of samples that are in class 1, but actually it is predicted as class J. Clear? Once again I will tell. The entry ij indicate the actual number of samples that are actually in class I but predicted as in class J. Number of samples that are actually in class I but predicted as that are in class J. Okay, so if this 1 2 the second one, the first row and second column indicate the number of samples that are actually in class 1 but predicted in class 2. Okay, so then depending on these values we have several terms. the class 1 can be considered as positive and class 2 can be considered as negative. Then the true negative means the first one is a true positive. Okay, we can discuss the first term, true positive. This true positive indicates the number of actual samples that are predicted as class 1. The number of actual class 1 sample, number of samples that are in the actual sample that are in class 1 predicted as class 1. Okay, that means number of predicted positive samples that are actually positive. And coming to the false negative, that means actually it is number of samples that are actually in class 1 but predicted in class 2. That means number of predicted negative samples that are actually positive. Then coming to false positive, FP, here the number of predicted positive samples, positive predicted as positive samples, but actually it is negative. Then true negative, here it indicates number of predicted negative samples and that are actually negative. And from this confusion matrix, it is clear that the actual result, the accurate results are from true positive and true negative, right? Because in true positive, the actually class 1 samples are predicted as class 1. And true negative, the negative classes that are actually, the classes that are samples that are actually in class 2 are predicted as class 2. Okay, so these diagonal elements will give the correct classification numbers. Then if we have two classes, our matrix will be 2 by 2. If we have three classes, our matrix will be 3 by 3. And from these confusion matrix, we can see that the correct predictions will fall on these diagonal elements in the confusion matrix, right? True positive and true negative are the correct predictions. So the correct predictions will fall on the diagonals of the confusion matrix and it is denoted by green O. And the off diagonal matrix, like represented by this cross, red cross, indicate the cases where the predicted value differs from the actual value. They are incorrect predictions. So in order to calculate the performance of classification model, we should consider all the counts in this confusion matrix, not only on the diagonal elements. We should consider both on and off diagonal elements. Okay. Then the classifier's accuracy will be the percentage of test instances that are correctly classified. That means the number of test instances that are correctly classified is sum of TP plus TN, and it will be divided by the average, divided by all the numbers, taking the sum of these four values. And error will be, of course, it will be 1 minus accuracy. And from this, again, we can define different terms like true positive rate. It is also known as recall rate or sensitivity. And a true positive rate is the number of samples, true positive divided by true positive plus Fn. That means number of samples that are the number of samples that are actually positive and but predicted as class 1. Okay, how many of that means how many of positive samples are actually correctly predicted as positive samples. That is that rate, that data we will get from true positive rate. The same thing, true negative rate, true negative divided by true negative plus false positive. That means how many negative samples are correctly classified as negative, and it is also known as specificity. The same way we can identify the false positive rate and false negative rate. And precision is true positive divided by true positive plus false positive. And recall, it is also known as true positive rate. And this false positive is known as type 1 error and false negative is known as type 2 error. This is the summary of the confusion matrix. And precision Precision means true positive divided by true positive plus false positive, which gives idea about how many positive predictions made by the model are actually correct. Model made some positive predictions. Among the positive prediction, how many of them are actually positive? The precision give this idea. And about the recall, it is also known as sensitivity or true positive rate. Here, it measures how many of actual positive cases recall. How many of actual positive cases will be were correctly identified by the model. That means true positive. How we have the actual positive cases. How among them, how many of them are correctly predicted by the model? That data we will get from sensitivity. Okay. Then coming to F1 score, it is a harmonic mean of precision and recall. In order to balance between the precision, and we can only focusing on one particular measure. So in order to balance these two measures, recall and precision, we can take the harmonic mean, and it is known as F1 score. F1 score combines both precision and recall into one metric, and it is mainly used upon the imbalanced data set, and high F1 score indicate the model performs well. And uh, then we can move to the receiver operating characteristic graph, ROC, and area under curve. Suppose consider the logistic regression. Here the x-axis shows the weight of the mouse, and y-axis shows the categories. We want to categorize the mouses into obese or not obese. So on the y-axis we have only two categories. Okay, then we have the data. This blue dot indicates the obese mouse. Actually they are obese, and the red indicate the mice that are not obese. Okay, then along the x-axis we have weight. Then with this, the this red color one, this mouse have the weight, high weight, but still it is not obese. It may be a mighty mouse with a full of muscles. Okay, again here the weight is less, but the mouse is obese because of its size. Okay, then we try to plot or fit a logistic regression curve to this data. Then in logistic regression, what we are doing, the y-axis will be converted to probability of obesity. Instead of classes, we will get the probability, right? And its value will be ranging from 0 to 1. But still, we want to classify the each mouse, right? Whether it is obese or not obese. So these probabilities should be converted into classification. So we select a threshold 0.5. Then we can say that all the mice with a probability greater than 0.5 can be considered as obese, and all the mice with a probability less than 0.5 can be considered as not obese. Okay, then here are the weights of 4 new mice, and we already know that these are not obese, and here we have the some data points, and we know that these are obese. Then if our threshold is 0.5, then according to the logistic regression, all these points with a probability less than 0.5 will be classified as not obese, and all these points with a probability greater than 0.5 will be classified as obese, right? So using these we can construct the confusion matrix. Here the column indicates actual and the rows indicate predicted. Okay, from this we can see that the actually obese things, here 4 obese are there, right? Among these four obese, 3 of them are predicted correctly. That is why we are putting 3. And one is predicted as not obese. That is why we are putting 1. And not obese case, actually we have 4 not obvious case. Among them, 3 are correctly classified as not obese. So we can write here as 3, and 1 is classified as obese. So we write it as 1. Okay. Then what happened? So can we improve this performance by adjusting this threshold? If we lower this threshold, what happened? Again, we will check the confusion matrix. In that case, if we increase the threshold, if we lower the threshold, we can observe that true negatives are reduced and false positives are increased. Okay. Then what happened if we increase the threshold? If we increase the threshold, again construct the confusion matrix, and we can observe that false negatives are increased and true positives are decreased. Okay. Then threshold can be set to anywhere in between 0 and 1. Then how do we determine which threshold is the best one? For each threshold, we can construct the confusion matrix. But checking for each threshold, constructing the confusion matrix and checking their values, it is not a good way, right? So in order to overcome that problem, we can use receiver operator characteristics. It is actually the card that in that it is a plot. Here x-axis we will draw the false positive, right, and on the y-axis we will plot true positive rate. Okay. Then this true positive rate, the y-axis tells you what proportion of obese samples are correctly classified, and the x-axis false positive rate tells you the proportion of not obese samples that are incorrectly classified, that is false positives. The true positive rate tells how many of the obese samples are correctly classified, and false positive rate how many of not obese samples are incorrectly classified. Okay. Then for if our threshold is nearer to 0, our true positive rate will be 1 and false positive rate will be 0.75. So initially this point 1 indicate the true false positive rate is 1, means the not all the not obese samples are incorrectly classified, and the true positive rate 1 indicate all the obese samples are correctly classified. Even if all the positive samples are correctly classified, but there are some, but not obese classes are incorrectly classified, right? Obese samples are correctly classified, but in not obese classes are all the not obese classes are incorrectly classified. So this point 1 it is not a good line. And this green diagram shows where this true positive rate and false positive rate are seen. And any point on this green line means that proportion of correctly classified obese and proportional of incorrectly classified negative or not obese samples are same. Okay, but our actually we did not require the points in this line. We did not require the model in which the true positive rate and false positive rates are same. Okay. Then suppose if we reduce the threshold, the point may change to this left side. Here the false positive rate is reduced. That means number of incorrectly classified not obese samples are reduced, and but the proportion of correctly classified samples that are obese is greater than proportion of samples that were incorrectly classified, right? Again, we can check with a different threshold, and for each of these threshold we can identify, we can plot the false positive rate and true positive rate, and area under this curve will give the idea about which ROC curve is better, which model will be the better, that you can be measured by the area under the curve. Then the best curve, this is the 2 curve, and from this 2 curve we can understand that the curve which is closest to the left side, left top corner will be the best model. Okay, the better model, in better model, when we try to draw the ROC curve, the curve should be very closest to the left top corner. Okay. Then again some key points. When the ROC is 1, then when the ROC curve will be looks like this, the area under the curve will be 1. That means the model have the ability to correctly classify the true negative and true positive. Then when the ROC curve looks like this, maybe the area under curve will be 0.7, right? So there is some overlapping. There are some misclassifications are occurring. That means 70% chance that model will be able to distinguish between the positive classes and negative classes separately. And suppose if our ROC curve is like this, here the area under the curve is 0. That means the model is not able to classify the positive and negative samples. They are not able to distinguish between these two classes. Okay. Then what are the evaluation measures for the regression model? We already discussed for the mean squared error MSE, and another measures are mean absolute error and root mean square error and R squared. Okay, in mean absolute error, we are doing is we'll take the average of the difference between the actual value and the predicted value. For example, if the mean absolute error is 1.155, means the prediction here we are taking the modulus value, right? So our predictions are wrong by either plus or minus from minus of 1.1555. That means from the actual point it can be either plus 1, the actual point can be either plus 1.155 unit to the from the predicted point, or minus from the minus 1.155 from the predicted point. Okay, then mean squared error that we already discussed. Here we are taking the average of squared differences between the actual value and the predicted value, and here we are squaring. So if the mean square is 1.6, we cannot say that our predictions are off by plus or minus 1.6. Okay, so we require the more specific one, square root mean square error. So we are taking in the square root of mean square error. In this case, if the root mean square is 1.2, that means we can conclude that our predictions are plus or minus away from the actual data points. Okay, then another one is coefficient of determination R square. Here it represents the proportion. This R square represents the proportion of variance in the dependent variable that is predicted from the independent variable, and it is calculated by 1 minus the square differences between the actual value and predicted value divided by square differences between the actual value and the variant, not mean. Okay, then 0.98 or value of R square indicate high level of correlation between the actual value and predicted value. That means high level of accuracy. That can explain 98% of variance in the observed data. Okay, these are the example. These are the evaluation measures used for regression model. For classification, we mainly use confusion metrics, and then in order to find out the in classification problem we can also use the receiver operating characteristic ROC and the area under curve AUC for measuring the quality of the models. Then in regression model we can use mean absolute error, mean square error, root mean square error, and R square. Okay, these are the different measures. So today we discussed the different we started with introduction to the machine learning and different machine learning paradigms such as supervised, unsupervised, and reinforcement. Then we discussed different supervised algorithms like classification and regression. Under regression we discussed linear, multilinear, polynomial, and logistic regressions. Then we discussed in between that we discussed overfitting, concept of overfitting and underfitting. Then in the afternoon section, we move to the different clustering algorithms, KNN, naive-Bayes, and XVM. Then we discussed the different measures that can be used for the evaluation of more models. So with this, we can wind up this today's session. And on Wednesday, we can do the hands-on on these algorithms.
Okay, ma'am. Thank you. Any queries from the participants?
Actually, I felt it's a one-way communication. Actually, it is first time I am taking the class on the whole day. Actually, I felt it is tiring, talking
Yes, it
continuously.
was. We were also feeling like it was somewhat hectic for you, ma'am. For us, it is fine.
I think if it is online, it may be more interesting. Like I felt like, yeah.
Okay. Okay, ma'am. Anyways, thank you so much.
Thank you, ma'am, for the informative and insightful afternoon session. Today's session provided valuable insights into how classification techniques are used in machine learning to categorize and predict outcomes based on data. Once again, I thank you all for your active participation. With this, we conclude today's afternoon session. We look forward to meeting again tomorrow for another enriching session. Tomorrow's session will be start at 9:30 a.m. Once again, thank you, ma'am, and thank you all.
Thank you so much, ma'am.
Thank you all.
Meet on Wednesday, ma'am.
Okay,
Thank you so much. Thank you all the
thank you.
participants for your active participation. Thank you so much. So be back tomorrow. Thank you.